So FTIR stands for what, Kevin?
Fourier transforming infrared.
Yeah. Okay. And let's just keep going. That works pretty good. So, Bradley.
Infrared energy?
Yeah. What is
Sorry,
it?
what is IR
Yeah.
energy? Infrared energy?
What is it?
Oh, it's on the electromagnetic scale
Oh, yeah.
above the Roy G bit. So it's on the
Well,
R to.
it's on the R side. So is that low energy or high energy side?
It's shorter waves, so that makes higher energy.
Shorter wave is higher energy. But if it's on the red side, Roy G Biv.
Oh, higher.
So red, which one is shorter wave?
Red.
Red is a longer wavelength than violet, right? So infrared's going to be even longer. So that would be an even longer wavelength, or what energy? Lower energy. Lower energy. Okay, what's a more common name for? I guess that's what I was shooting for. That's the technical answer you gave. But what is it? You want to generate IR energy in this room. What would you do? You want to have a little IR light source. Put it right there. What would you do? What's a more common name for IR? Infrared, but what? The layman's term. Starts with an H. Heat. Let's have a heat source. Right? Like a great source for IR energy are those burners, you know, that you go cook in the stove and you turn it on, it starts glowing. Excellent IR source. Okay. It's so hot, it's starting to emit Roy G. Biv instead of just infrared. So that's why I say it's so good. Estacio, the next one.
Why is there a break in the scale in all FTIR spectra at 2000?
Now, first, can you see the break in the scale, right? Because you go from 2,000 to 3,000, that's 1,000. But then you go below the 2,000, now it's 1,500, right? This looks like it's 500 here, right? They changed the resolution on you. That's what I mean by breaking the scale. Right at just convention, at 2,000, they always do that. Why do they do that? Anybody know? Or you can detect a lot, right? Because they're zooming up on this. This is 500 now. Before it was 1,000, so they really increased the resolution. It's kind of like taking that scale and just spreading it out twice as far, right? So if you on the right-hand side, it's this wide, but on the left-hand side, it's this wide. Right-hand side, just spread it out twice as far. There's a lot more signal. They call that the fine structure region.
So the break in the signal is the fine structure?
Because below it, that's where you get a lot of these little, you've heard of these stretches, right? The NH stretch. A lot of those sorts of stretches, you find them down here. All those tabulated values of vibrations and their corresponding wave number. Yeah, a lot of them fall down there. So that's why it's easier to pick them out if you spread it out more. Okay. Shelby. Mm-hmm.
Okay. Are we going to do all the vibrations?
What is a dipole?
Yeah. What is a dipole?
Sorry, I skipped that one. I didn't see it.
What is a dipole?
Like dipole? Are we talking about like in dipole moments?
Good. Those are all the same word.
Yeah.
Dipole moment, polar, all synonyms. Mm-hmm. And what is the difference? Is it charge? We're talking about charge, right? So a dipole is going to be a separation in charge, right? And it might not be, and it's not ever. We're talking about molecules, not ionic compounds. So we're not talking about plus and minus. We're talking about how do they indicate changes in charge. You could do little colors. A lot of computer modeling does that for high electron density. And then for low electron density, but come on, we're not going to be doing this. What do you do in general chemistry to indicate polarity?
On one side, negative on the other side.
Partial. Oh, sorry. Red is negative. Okay. Do you remember what created these dipoles? Difference in electronegativity. Andrew, what was the most electronegative element on the planet? Fluorine. Yep. Okay, so that's how you create your dipoles. Differences in electron.
Question and answer.
What's the most electronegative element on the planet? Here's some examples of why there's a lot more stretches in that fine structure regions. That's another reason why they really zoom it up more. That's a good example of the table. Okay. Eric, we're on do all vibrations absorb IR energy?
I want to say no.
Well, a good hint is the next question, right?
Yeah, I guess
So,
no.
yeah, the answer is going to be no, because there's something called an IR active vibration. So that really leads us, Kevin, to what is an IR active vibration? Yeah. No, okay, but it's IR active. What makes it IR active? You have to have, what's that? Oh, yeah, that's the vibration. That's the vibration. But not all of those are going to be IR active. Something has to be occurring for it to be an IR active vibration.
They can't be the same. It's what was the word you use when you described it?
If
They can't be like these cancel each other out. They have to be asymmetric.
you're getting there.
Movements.
Good. Okay, that helps. Maybe if we just say the word first, that might help you visualize it. IR active vibration. They all have something in common. They all have an oscillating what? Dipole moment. Or just say the word dipole. Same thing. They all have an oscillating dipole moment, or an oscillating dipole. Okay. If you don't have an oscillating dipole, it can be a polar molecule, but if that dipole is not oscillating, it won't be IR active. So we'll have some examples down here so you can pick them out and see what I mean. It's kind of hard to visualize that. But here's several types of vibrations and what they mean. Like when they say symmetric stretch, they're talking about both atoms moving out at the same direction at the same time, right? Asymmetric, not so. One's moving in the maybe not the opposite direction, but they're asynchronous, kind of like in-plane rocking, in-plane scissoring. Okay. Jeez.
All of these are IR.
No, dude. These are just examples of vibrations.
Okay, but
So whether it's an oscillating dipole or not, you need more information. So we're going to get you that more information when we start showing you some vibrations. Okay.
so is that asymmetric bond movement correct?
These are all just types of vibrations. I'm not saying they're IR active or IR inactive. They're all just types of vibrations.
I'm sorry, my question is, when it asks what is an IR active vibration, is that determined by asymmetric bond?
No. The answer is right here. It works every time. I mean, your answer could work, but I'm just saying there might be special cases where that answer is wrong.
Okay.
So this answer always works to describe an IR active vibration. Have an oscillating dipole. And you'll be able to picture this when I start showing you some vibrations.
Okay.
But right now, you just have to take that as the answer.
Okay.
Okay. Allowed energies of vibrations. Should have probably talked about this first, but that's okay. So pertaining to this figure, I guess I'm on Bradley here. A chemical bond. A chemical bond is mathematically
Allowed energies
Oh, hoo-hoo. Yes.
K is a spring constant or force constant.
Very good. All right, F equals kx.
Get it, Brad.
All right.
Equal Lola.
How about Estacio? Next one. What is different?
What is different between two bonds when one has a larger K value than the other? Do they have different vibrational energies?
Yeah, but yeah, they will. It'd be different force, but I guess, and that's, I don't have two of these. So if this guy oscillates like this, and he has some spring constant, F equals kx. So more force, more distance, and k is just the constant. If I replace this with a really stiff spring, that means that I'd have to use a whole lot of force to stretch it just a little bit, right? So that means my k would be really, really big. That's a really stiff spring. Okay, I wish I had one, because that's the answer. If I could have a spring that was really stiff, and then I pull it down a little bit, maybe you can imagine it. Is the oscillation going to go faster than this, or would it go, or would the frequency be smaller?
I think it could go faster.
It's kind of,
It's like, yeah, it's almost like a spring. If it's harder to pull it apart when you let go of the spring.
it's going to zip back even harder. Exactly. The force is higher. So you crank up K for those bonds, those frequencies are higher, right? They're oscillating at a higher frequency, whatever the vibration is, right? The oscillation is at a higher frequency. So that's really the answer to that. And I need to get in order to demonstrate it to you, I need a stiffer
So we just say
spring.
stronger bond.
What you could say, a stronger bond. Exactly. You could say stronger bond,
And we could explain that by saying there's a greater force between them.
greater force between them because of, and with this model, if you're going to model that bond after a spring, the technical jargon would be the spring constant is bigger. But stronger bond works. It takes more force to stretch it. It takes more force to stretch it. Man, it's going to zip back even harder then when it does stretch. Shelby, are vibrational energy levels evenly spaced?
They look spaced in the picture,
Yeah, right? Yeah, they look evenly spaced. Okay. So let's just keep going before I keep.
What about between like the top ones? They look like they're closer than the bottom ones.
The oh
Like from 654.
yeah, they didn't draw it very well. It's just no, they're equally spaced. Okay. The what's odd is that this well, this potential energy well, right? Here's all your states. You're saying that there can only be certain excited states for that oscillation. There can only be certain excited states for this spring. Well, no, not for me. I mean, I can pull this down whatever distance I want. I can pretty much give it whatever energy I want. I can give it a little dinky bit. I can give it a lot, right? There's a continuum of energies. But this is not a microscopic particle. If it was a microscopic particle, it's weird. It can only oscillate, it's going to look weird. It can only oscillate like this. It can only oscillate like that, right? These distances, right? You're just changing those distances that it can be oscillating between, the amplitudes. Anyway. Oh, Andrew, each type.
Each type of vibration has its own individual set of length levels as illustrated in the above diagram.
What are they calling them?
Quantum levels?
Yeah, quantum or vibrational energy levels, whatever word you want to put in there. But it refers to just one vibration, right? One stretch. Each stretch vibration is going to have its own ladder, okay? If you want to call it vibrational energy levels or whatever. So each stretch does, okay? Eric, vibrational energy levels.
Vibrational energy levels look like an energy ladder. How does a vibration travel up this energy ladder?
Yeah, stop there.
How does
And that energy has to exactly equal what?
The distance between the two.
Yeah, the energy difference between the two. Because this is energy going up. So you just figure out what, like if you want to go from V equals 0 to V equals 1, figure out what this energy is. Figure out what this energy is. Subtract the 2, that's delta E. That has to equal, well, h nu, or hc over lambda, right?
It absorbs the energy. Well, it absorbs energy, and then you said that the energy that it absorbs is like the difference between each and
Yeah,
each.
so the energy has to actually match. Now, what region of the electromagnetic spectrum is that difference in energy? Infrared, heat. Okay, it's in the infrared region. So see if Bradley remembers this, right? Because we have, you see this? Inverse centimeters. What do we call that?
That's the wave
That's wave,
function.
anybody remember? Wave number. That's wave number. Okay. And the energy of a photon is h nu.
The wave number changes?
Wave number is inverse centimeters. That's what you're plotting in IR spectra. That's just their convention. I don't know why. They could have been wavelength, but in IR they like wave numbers. So that's just how it is. Okay? And what I'm trying to do is describe what a wave number is, because you have an idea what a wavelength is. So the energy of a photon was h times frequency.
Oh, okay.
And frequency is c over lambda. Wave number is in here.
So wave number equals.
What does wave number equal? It's in there. Now the hint is it's inverse centimeters.
So it'll be the wave length.
It's
So is it the C over the? Oh wait, would it just be this?
it has to be whatever you pick has to have units of 1 over distance.
Centimeters on the bottom, which would
Has
be
to.
your frequency, right?
So it's just that gamma, the
Real
whatever the
lambda.
gamma.
You don't see it. I'll have to tell you. Hc times 1 over wavelength. Right here. Doesn't that have
That's what making it.
doesn't that have units of inverse distance?
Yeah.
Yeah, so that's all a wave number is. It's 1 over wavelength. But not in nanometers, but in centimeters. It's just their convention. Maybe because it spreads things out nice. That's probably why. Because when these guys get their spectra, they want to be able to pick out peaks in this fine structure region. So I think this is just works out really well. If you don't plot versus wavelength, plot versus wave number, in centimeters, things start spacing out pretty good. I guess that must be what happens, right? Because they didn't have these nice computers where you could draw a box and stretch and zoom. Okay. So now we're just stuck with it. We're not going back. Let's see.
So if we take the wave number that we get from there and just multiply it by Planck's constant and the speed of light,
Oh, if you want to,
we'll get the energy function.
if you want to get energy, well, it depends on what units you want for energy. If you want to stick with the metric system, energy units are joules. Well, then use the Planck's constant and make sure it's in the metric system, joules in seconds. C, make sure it's in the metric system, meters per second. Wavelength had better be in, not if you want joules.
So you want meters.
It has to be in meters. If you want to work in, there's all these other,
Oh,
but
I see. So
so
if we take that number that it gives us off the IR spectrum.
that's just 1 over wavelength, but in units of
Centimeters.
inverse centimeters.
But you
Yeah.
take the inverse of meters.
Yeah, if you want to actually calculate the energy in joules of this stretch, you'd have to put everything in units of standard metric units,
Plug and chug.
and then plug and chug. Okay. So those energies have to match, the difference in steps, if you're jumping from one to the other. Okay. So Eric told us that if you're going to travel up that ladder, you have to just absorb the energy difference that we talked about right here. Okay, back to Kevin. What do you think?
What do you think is different about vibration
Yeah, just stop there. What changes?
Potential energy.
Potential energy changes, but if you're just observing that vibration, you're just observing the vibration, it absorbs the right energy that matches its vibrational energy ladder. What would change in that vibration? What would happen differently? Has to be more energetic somehow, right? Because it absorbed energy.
So more heat is applied.
Same thing happens here, right? This is oscillating right now. Now, I know it's not microscopic, so I can apply any energy I want, but it's the same idea. So I apply some energy to it. Did I change frequency? Yeah, I didn't change frequency. I just changed what? Amplitude. Yeah. It's coming back. So I changed the amplitude. And I could keep changing the amplitude and give it so much energy, and finally it's going to break the bond, but no, I'm not giving it that much. Right? I just changed the amplitude. So what is different about the vibration as it travels up the ladder? What changed? The amplitude of the vibration. What stayed the same? The frequency. Okay. Now, I don't think we even talked about this in P-Chem yet. I just have to give you this answer. Vibrational energy levels are numbered using a quantum number V. We solved the Schrödinger equation for that, but that's a little too much information. For transition to occur, this delta V has to be plus or minus 1. This is an example of a selection rule. So you can't do any transition you want. You can only have a delta V of 1. That's the only transition that can occur. Up or down the energy ladder by 1. So how many different vibrations can a molecule have? It depends on the degrees of freedom. So how do you get this? There's only so many points to describe something. So 3n is a total number of degrees of freedom. And n is just the number of, we're talking about a molecule. So for just to describe one atom's location, you need an x, y, and a z in that molecule. But a molecule, if it has 3 atoms, well, then you have x, y, and z for each of those 3 atoms. N is going to be the number of, see where I'm leading? Atoms. N is the number of atoms. So 3n is the total number of degrees of freedom. And it describes the number of points required to describe the molecule's location in space. Because each atom needs an x, y, z. Okay. Subtract 3 of these, you lose 3 degrees of freedom when you use to describe the molecule's translation in space. And then you're going to lose some more degrees of freedom. So what's going to be left over is the vibrations. But you lose some more, either it's 3 or 2, whether the molecule is linear or nonlinear, to describe its rotation in space. So this always works. The number of vibrations for linear molecules is going to be 3 times the number of atoms in that molecule minus 6, if it's linear. Sorry, if it's nonlinear. If it's linear, it'll be 3n minus 5. Because, okay. Oh, here, we'll show you. Let's do one. If we have water, water, before I even click on it, is water linear? How do you know water's bent? You remember doing this? We called it the Vsepper theory. Man, he's got a memory on him, right? H2O, right? 8 valence electrons, right? You put O in the center. You put the H's on there. First step was to count up the number of valence. This is an easy one, but it goes through the same steps. You have 8 valence electrons. Everybody agree? Oxygen 6, each hydrogen 1. So first thing, make octets on everything surrounding. Any electrons left over, put them on the center atom. Well, hydrogen is, once you connect it, he's got his octet. It's only 2, but he's matching what noble gas? Helium. So he's done. So hydrogen's done. I only used up 4, so I have to do 2 more. Okay, so you think, oh man, I guess maybe I put them down here. Make it linear. No. Check out Kevin's Bicep theory. Valence shell electron pair repulsion theory. The tetrahedral shape, because you have 1, 2, 3, 4 things. That's where this is really coming from. It's coming from nature. If you have 4 things, what's the lowest energy to arrange 4 objects?
What's that?
If you have 4 objects, all identical, what's the lowest energy to arrange them in space? Because they all have to be connected.
Oh, equidistant.
Tetrahedral shape. Tetrahedral shape. So it ends up looking like, I don't know, something like this. Okay. So you put your lone pairs. So Vicepper is all about that. You spread out your electrons as much as you can. So you have this tetrahedral shape. So I don't know, right? Spread them out as much as you can. You end up having a bent water molecule, right? It's supposed to be an H. See, you remember this kind of thing? Had these wedge drawings where this is a wedge that's coming straight out of the paper. The dash is going straight back. Okay. So water's bent. So how many vibrations should water have? This part would be 3 times 3 times 3, because there's 3 atoms. Okay, so you have 9. And now am I going to subtract 3 for translation? Now do I subtract 3 or 2 more? Is water linear? No, it's bent. So subtract 3 more. 9 minus 3 is 6. Minus 3, I'm left with only 3. So water should have 3 vibrations. Let's see if the little model came up with 3. There they are. There's the 3 vibrations for water, and their corresponding wave numbers. Okay. All right.
It's like a little guy like exercise.
Yeah. So let's get one with more here. So what we want to do is we want to take a look at these vibrations and see if we can find ones that will not absorb IR energy. Okay? Now I know there's one in CO, if I remember right, CO2? Okay. Yeah. Okay. Does CO2 have any vibrational modes that will not absorb heat? They're a vibration, but they will not absorb infrared radiation.
The first one is not right.
Now you have to find something that does not possess a what? What did we say? It can't have a oscillating dipole. Can't have an oscillating dipole. What the heck?
So since that person stays like stationary,
Okay.
it doesn't have an oscillator.
So this first one, if you guess this first one, you're right. Because at every moment in time, those dipoles are canceling out. Right? Every single moment in time, they're canceling out. Are they canceling out here? No, this is an oscillating dipole. Are they canceling out here? Oh, oscillating dipole. Here's AuCO4. Do you see any here that are IR inactive? IR inactive.
First one, second one, fourth one, fifth one. Not the third one.
6th one and 7th one.
Okay. Do we agree with this one? What do you say about the top? What do you say about the top one? How do you get it to repeat? Is that one? All right. We all agree with the top one. IR active. Inactive. IR inactive. IR active?
Inactive.
Man, maybe you're right. I was first looking at that thinking that would absorb IR. But yeah, I think you're right.
But just looks like they're
All
counted.
right? Because I think they're countered the whole time. They're going to cancel out the whole time. How about this one?
IR active.
Yeah, that'll definitely absorb IR. So I think you got the idea, right? I don't know how you
As long as that middle element counts.
turn repeat on.
What about the middle one? 6?
This one?
Would that be inactive?
So these two,
Those are canceling and those
they're
are canceling.
can
They're not all canceling.
yeah, I think these are canceling and those are canceling. That should be IR inactive. Yeah. Yeah, because I think if you just isolate it, okay, so that's the game you're playing for this IR active, inactive stuff. There's a bunch more. There's this one if you want to cross your eyes. It's supposed to look 3D. I don't know if that actually works.
Cross your eyes.
Yeah, if you look cross-eyed, it's supposed to look 3D. Okay.
Yeah.
Did it work? You didn't do it.
You did do it.
You give us enough time.
That's gross. I don't want you to. You'll stay that way. That's what my mom always said.
No, I always heard that if you cross your eyes, someone hits you in the back of your head, you'll stay that way. I'm serious. And so
All right.
My mom said, my mom said, no, that was 1 year.
So how does a FTIR spectrophotometer get an IR spectrum? So you start with your light source, pretty much a glow bar, and then it jumps into an interferometer. Probably one of the most sensitive instruments available, which Bradley is going to make in PChem. You're going to make an Michelson interferometer in lab. You can, if you watch really closely with a Michelson interferometer that he's going to build, you could, this building is shaking a lot, but if you could stop closing all doors, flushing all toilets, and then just close one door, you could detect it with this thing. It's that sensitive. It's crazy. But you're going to...
It's going to be expected to get those types of results.
So the point is that this mirror moves back and forth, and it makes an interferogram. All that is just changes in intensity, and it's really hard, I think, to picture this without actually seeing it. So maybe when Bradley makes it, like we already saw his monochrometer, when he makes the interferometer, we'll just leave it over there so you can actually see what an interferogram is and how it changes with changing that mirror. But they're going to move that mirror back and forth, and that's going to get changes in the intensity, get an interferogram, okay? So that goes through the sample. So you're going to, either some frequencies or some wave numbers are going to get attenuated, others not. Depends on what stretches are going on there. You need to do this twice, so you need to get a background, because remember absorbance is transmitted over incidence, so negative log of it. So you need to get both. So you measure your background, and then you put your sample in, do the same thing, okay? And then take the log, you'll get your spectrum. Oh, sorry, I went the other way, going this way, right? Okay. The computer needs to do this fast Fourier transform to go from this intensity with distance, how that changes with respect to wave numbers and what's present. There's a lot of, right? There's all wave numbers are here. All frequencies. Well, you can call it frequencies, you can call it wavelengths, you can call it, right? They're all there from that light source. So all at once, all that information is in a very odd way. It's in that interferogram. So, but it's in a realm that you really can't relate to, with intensity and distance. So if you do the Fourier transform, you just change domains. You change domain from that time. How does the intensity change with time to frequency? Okay. Things that you can analyze with the FTIR. Okay. You've done liquids. I think we're going to do some powders. We've done this kind of thing to see what's thrown on the beach in Texas. Okay. But there's a lot you can analyze with it. That's all I have. Yeah, micro. There's a poster on it. So this is in excess, but usually you're just looking for these little tiny pieces of plastic that are building up in the environment. They call them microplastics.